Hello and Assalamualaikum to panels and all viewers of this presentation. My name is Muhammad Azri Fikri bin Arbain, a finalist student of Mechanical Engineering at UiTM Shah Alam. In this presentation, I will present about my final year project, which entitled Synthesis of Eggshell-Derived Calcium Phosphate Powder via Solid State Reaction. The study is under supervision of Dr. Natasha Ahmad Nawawi and Dr. Rozlin Masdek. So I will continue with introduction. Calcium phosphate or CAP is the main mineral found in human bone and teeth. An example of calcium phosphate is hydroxyapatite or HA. Hydroxyapatite is one of the most stable calcium phosphate which is usually used in medical application, especially in orthopedic and dentistry. The reason why HA is preferred to be used is because of its properties, which are good chemical and thermal stability, distinctive absorption capability, and it is biocompatible. Hydroxyapatite has been actively used in bone repair and regeneration, dental implant, and drug delivery system. Calcium phosphate can be synthesized from either commercial chemical or organic source of calcium. However, it is much preferable to use organic source due to lower cost and higher sustainability. Examples of organic source of calcium are animal bone, seashell, coral, and eggshell. Eggshell is one of the most preferred natural calcium sources as it consists of 94% of calcium carbonate and due to its sustainability as compared to other natural sources such as coral, which can lead to extinction when overused due to its low growth rate. There are various methods to synthesize calcium phosphate, for example solid state reaction, wet precipitation, salt gel, hydrothermal, and mechanochemical methods. Solid state reaction is one of the most preferred methods due to its suitability for mass production and there's no need of precise control condition. Next, we will be moving to problem statement. In CAP synthesis, precise control of crystal growth presents the ultimate challenge because it directly relates to the characteristics of the final particles such as grain size, material crystallinity, and geometric shape and distribution. These primary characteristics subsequently affect the mechanical properties, biocompatibility, and bioactivity of the produced calcium phosphate. Hence, the mixing methods during synthesis became among the important factors to be observed as they directly influence the characteristic of final CAP particles. The study consists of three objectives, which is first to synthesize Eggshell-Derived calcium phosphate powder using the solid state reaction method. Second, to determine the appropriate mixing parameter. And lastly, to study the effect of magnetic stirring method on phase stability, morphology, and particle size of the synthesized calcium phosphate powder. The scope of the study is entirely based on experimental works. The CAP powder was produced using the solid state reaction method. Eggshells was used as the source of calcium, and lastly, this study only observed the effect of magnetic stirring and various calcine temperatures, which are 600, 700, and 800 degrees Celsius, towards phase stability, surface morphology, and chemical composition of the produced CAP powder. Next, we move to methodology section. This is the flowchart of the sample preparation. For sample preparation, the process was divided into two parts, which are eggshells calcination and solid state reaction. It started with collections of waste eggshells and clean it to remove the inner membrane layer. The eggshells was then be crushed and ground using pestle and mortar. Once become a powder, it was subjected to calcination at 700 degrees Celsius for 1 hour to obtain pure calcium carbonate. After that, by using conventional magnetic stirring, The calcium carbonate was mixed with the calcium phosphate dehydrate at a CAP ratio of 1.67. The magnetic stirring was operated at 400 rpm for 2 hours with addition of ethanol as a solvent. Once mixed, the mixture was dried at 110 degrees Celsius for overnight. The dried powder was then sieved and subjected to heat treatment at 3 different temperatures, which are 600, 700 and 800 degrees Celsius with 10 degrees Celsius per minute of heating rate. Once reached the desired temperature, the powder was then applied to 1 hour holding time and let to cool naturally. Next, for the analysis part, we are using X-ray diffraction XRD to obtain information about the structure of crystalline materials. The sample was carried out at room temperature, operated at 40 kV and 40 mA using copper potassium alpha as the radiation source. The X-ray size was 0.02 degree with the scan angle varying from 20 degree to 50 degree. Next, we move to observation of surface morphology and elemental composition. We are using a scanning electron microscope (SEM) equipped with energy dispersive X-ray (EDX) to observe microstructure and elemental composition of the samples. The sample was examined under SEM at an accelerating voltage of 5 kV at magnification up to 5000. The sample was coated with platinum to minimize the charging effect, and 4 spots were chosen randomly to observe the sample elemental composition for EDX. Next, we will be moving to results and discussion. First, we will be discussing the XRD analysis. The figure represents the phase stability of samples calcined at 3 different temperatures, which are 600, 700 and 800 degrees Celsius. There were presence of hydroxyapatite and beta-3 calcium phosphate at all 3 calcination temperatures, according to JCPDS of hydroxyapatite and Whitlock. At the calcination temperature of 600 degrees Celsius, it shows a relatively low presence of both HA and beta-TCP. However, the presence of beta-TCP started to increase when the calcination temperature increased to 700 degrees Celsius. Lastly, at calcination temperature of 800 degrees Celsius, it shows a strong peak of hydroxyapatite phase. From the result, we can conclude that the crystallinity of biphasic calcium phosphate, which is a mixture of HA and beta-TCP, increases as calcination temperature also increase. Next, we will be moving to the particle size calculation. Average particle size of samples were calculated by using data obtained from XRD analysis and Scherer's equation. To calculate the average particle size, information from the 4 highest peaks has been used for every sample. From the table, it shows a decreasing pattern of particle size as the calcination temperature decreased, with 0.241 micrometer is the smallest particle size obtained at 800 degrees Celsius of calcination temperature. This finding is in good agreement with the fact that particle size decreases as the breadth of the compound main peaks increases. This is the result of EDX analysis. The figure represents the elemental composition of samples calcined at 3 different temperatures, which are 600, 700 and 800 degrees Celsius. All 3 samples consist of calcium and phosphorus with a trace amount of oxygen, which might come from the base used to mount the sample at the machine. Calcium is necessary for bone growth, where it will help strengthen the bone, while phosphorus helps in bone absorption. Next, from the result of EDX analysis, the CAP ratio also can be calculated by using the element weight percentage of calcium and phosphorus. CAP ratio represents the phase shift between tricalcium phosphate (TCP) and calcium oxide (CaO), which means the HA with a higher CAP ratio, it contains more TCP and CaO. The CAP ratio of 1.53, which obtained at 700 degrees Celsius calcination temperature, was the nearest to the expected CAP molar ratio, which is 1.67. According to the study done by Bano, the calcination temperature should not affect the CAP ratio of the produced calcium phosphate. Formation on biphasic calcium phosphate powder might be due to insufficient mixing time for the mixture to completely react to form pure HA during the solid state reaction. The last result that will be discussed will be the SEM analysis. The figure shows the microstructure evolution of the samples, where the top one indicates the magnification of 1000 and the lower one are the magnification of 5000. As you can see, the uppercase of ABC at the top indicates the calcination temperature, which A is for 600 degrees Celsius, B for 700, and C for 800 degrees Celsius. At calcination temperature of 600 degrees Celsius, it shows that the SEM image resembles needle-like particles but started to agglomerate at 700 degrees Celsius. And at a temperature at 100 degrees Celsius, SEM image shows that the particle agglomerate to form an irregular shaped structure. According to the study done by S. Ramesh, it shows that the dispersion of particles by using the magnetic stirrer was not as good as attrition milling. Also proven by A. Zakvari, the attrition milling can produce a smaller particle size mixture as well as good dispersion, and it takes a shorter duration to complete the process. And lastly, the conclusion and recommendation. The solid state reaction of waste eggshell as calcium precursor and decalcium phosphate dehydrate as phosphorus precursor via 2 hours conventional magnetic stirring method followed by calcination of the mixture has produced biphasic calcium phosphate, which is a mixture of HA and beta TCP. The finding concludes that 2 hours duration of magnetic stirring mixing might somehow be insufficient for the calcium and phosphorus precursors to completely react in forming pure hydroxyapatite. For further work, the mixing duration can be prolonged to confirm this expectation. This is the references that have been used to do this slide, the presentation slide. That's all from me. You can contact me at through my email at azri@gmail.com or through my mobile number, which is 017-626-9590. That's all from me. Thank you.